Okay, today's topic is geometrical structure factor. Our previous lecture is atomic structure factor, and that is related only to a single atom in respect with their electrons. But here, geometrical structure factor. Geometrical structure factor, it is due to the whole unit. I can write that here we are discussing the amplitude of radiation scattered by the entire unit cell to the amplitude of the radius scattered by an electron placed at the origin. Okay. So the intensity of an X-rays from the crystal not only depends upon the atomic scattering factor of various atoms involved, but also depends upon the number of atoms involved, type of atoms, and the distribution of atoms within the unit cell. So mathematically, I can say that the total scattering amplitude, which is defined as the ratio of the amplitude of radiation scattered by entire unit cell to the amplitude of radiation scattered by an electron placed at the origin. So unit cell may be three types. For example, if we have the cubical unit cell is there, then it may be like simple cubic, then BCC, body centered cubic crystal unit cell, and it may be like FCC, face centered cubic unit cell. So if here the structure factor is depending on the geometry of the unit cell. So I am replacing atomic scattering factor by geometrical structure factor for this. So now see in the second uh, in the second equation we are we have this yes, this is this one. So we can write that f h dash k dash l dash that equal to f1 exponential iota phi 1 f2 exponential iota phi 2 plus f3 exponential iota phi 4, where fj's, that is in generalized form we can write it summation j fj exponential iota phi j. We can write this in the summation form. Fj is the atomic scattering factor. This is the atomic scattering factor of the jth atom, and phi j represent the phase difference between the jth atom and of the unit cell and that scattered from the electron at the origin. So we can say that if we have some the unit cell is like this, and let this is your simple cubic, then the atomic atoms are at the corner like this. So if these are at the corner, then there is a scattering when X-ray strike this, then there is a scattering for this. There is scattering for this. X-ray strike the atoms and scatterings like this, scatterings like this. From the whole fraction of the atom, there is a scattering, and I have the total scattering. I have the total scattering from the unit cell. So this is the basically we have to find. So this is the topic of the day, that we have to see the geometry of the unit cell, and then the total scattering from the that particular geometry. If we have this this is our first one. If this is your primitive cubic crystal lattice hai, this is all the atoms are at the corner, then we have some, this is the scattering of the X-rays from all the atoms. We have to calculate like this. So for this reason, I am saying that F1 for the first atom, this is for the first atom, this is for second atom, this is for the how many atoms are present in the unit cell. So in the total sum of the scattering, that is the total scattering of scattering amplitude of the radiation that is emitted from the unit cell. Okay, if this is the second time, then this is BCC, then there is a 1, this is 2, this is 3, this is 4, 5, 6, 7, and 8. 8 atoms at corner, so it is 1 by 8. Then the total atom is equal to 1 atom plus 1 is at the inside the body, that is the total atom equal to 2. So number of atoms here equal to 2. And in this, the total atom is what? If this is the face-centered cubic crystal lattice, if the geometry is like this, then we have 1 by 8, 8 atoms at the corner plus face. Face, there are 6 faces, 6 atoms are there. These atoms are at the faces. These atoms are at the faces. So 6 by 2 plus interior 0, that equal to, this is what, 1 plus 3. There is 4 atoms for the FCC. There is the scattering level is different because here we have the 2 atoms, here we have 4 atoms, here we have 1 atom. So scattering amplitude will vary according to the number of atoms and as well the distribution of the atoms in the unit cell. So the very first step that we have to take for this, that is the phase difference phi j. This is 2 pi by lambda rj dot n vector, rj vector dot n vector. This is we have taken from the Lewis equation, and from Lewis equation we have taken that delta phi, that equal to 2 pi by lambda multiplied to delta x phase, that is the path difference. This is the path difference. So by making use of this concept, we are able to find this equation. So this equation is for your phase difference. Here rj vector represent the position vector of the jth atom and n vector represent the scattering normal. So on putting in the equation number 1, this is our first equation. I am putting this value. So this is the value for phi j you have to write here. So this is f h k l dash equal to this. F capital F equal to fj summation and exponential iota 2 pi by lambda rj dot n vector. Okay. In the second step, I want to find this term rj dot n vector. So rj I am taking here uj a vector plus bj vector plus wj vector. Okay. So uj, vj and wj, they are representing the scalars. This may be 1, this may be 2, this multiplied to the lattice primitives a, b vector and c vector like this. So we have done in the second equation, we are putting the values a dot n is like this, and we have this. So from also, this is also from the Lewis equation. Again we have this Lewis equation, a dot a vector dot, and that is h dash lambda, b dot that equal to k dash lambda, c dot n vector that equal to l dash lambda. On putting these values in the previous equation, we have uj, and I am putting this value here, uj, that h dash lambda, b this is k dash lambda, and this is c, and this is w dash lambda. So we are here. I am taking lambda outside the bracket, so it is uj h dash, vj k dash, wj l dash. Okay, and lambda outside the bracket, and this is uj h dash, bj k dash, wj l dash. So we have this term is this. On putting this value, there is this value is here, rj dot n vector is here. I am putting the value from the equation 6 here. So we have this equation is like this. If this equation like this, then I am seeing that this lambda can be cancelled out by this, and finally we have equation number 7 is there. So it is iota 2 pi uj h dash plus bj k dash plus wj l dash in the exponent. Okay. So if all the atoms are identical, then I can write that the atomic security factor for all atoms that can be replaced by F. So taking F outside the summation, we have iota 2 pi uj h dash vj k dash and wj l dash. So finally I can write this equation f h dash k dash l dash f dot s. I am considering this the whole term. I am considering the whole term, this term that equal to s, and this is your f. So finally we have this equation. So where s, this term exponential iota 2 pi and vjk dash, this is your geometrical structure factor. Geometrical structure factor is this. So this is the geometrical structure factor and depends upon the arrangement of atoms within the unit cell. So it means it vary from the simple cubic, BCC and FCC have different values. Okay. So step number 3, calculation of intensity. So intensity of the diffractive beam is given by, this is F star F, because intensity is directly proportional to amplitude square. Amplitude square. So in terms of amplitude we have F. So F, I can write this F star F. So intensity will be like this. So I am abbreviating the intensity in this form. So when you do that, this is your complex term. So I am replacing the iota with minus iota here. So after that, applying this, I know the formula that exponential iota theta equal to cos theta plus iota sine theta. And if it is if in the second minus, then it is minus. So on applying this, I will be cos, this is theta plus iota sine theta cos, this is theta minus minus, and this is sine theta. So in the next step, what we have, now we have to see this whole equation like this. This is A, this is V, A plus V, this is A, this is minus, this is V. So this will equal to A square minus V square. So if this is the term, then what? This is A plus V, A square. What is A? Cos 2 pi UJH BJH. Okay, this is A minus A square minus, this is A square, sorry, there is A square minus this, and when we are here, then we have, this is the square of this is A square, and minus this is plus, and this is B square is there, like this. The system is, we have the system is like this. We have the system like this. So if these are the terms, then we have this is the total intensity of our expression. So we are able to calculate it. Now the special cases, we have the two special cases. Case 1, if I have the simple cubic crystals, then the effective number of atoms, that is 1, and if it is 1, assuming that this atom lies at origin, then this is the values for this. On putting these all values in the previous equation, here we have Uj, that is 0, Vj 0, then Wj 0, Uj 0, Vj 0, Wj 0, then something we have, this is sine of 0, that is 0, this is cos of 0, that is 1, like this. So in the final expression, what we have, we are getting exponential 0 is there only, and exponential 0 equal 1 and f. So if this is your f value, so intensity will be f square plus from where we are putting here app like this. We are putting here use a bj. Yeah, we can see that this is we are putting this value here. We are putting use a vj and wj equal to 0 in this equation, and finally fj equal to f. So we have this equation. So this is f, so intensity will be, this is f square plus f into 0, this is f square plus 0, that is f square. So this will be the relation for simple cubic crystals. This is the case for 2 when the effective number of atoms is equal to 2. For BCC case, we have BCC, we have the atoms are there at the corner, they are at the corners, atoms are at the corners, as well as one atom is inside the body, like this. This is the case. So these are the coordinates. Atom lies at the origin 0 0, other lies at the body center position 1 by 2, 1 by 2, 1 by 2. So we have the coordinates like 2. These are the my because from there to there the distance is half. If this is your 0, this is distance is half. From here this is also half. From 3-dimensional this is also half. So the coordinates are 0 0 0 for first atom, and for second there is half, half, and a half. Atom number 1, atom number 2, like this. These are the coordinates. If these are the coordinates, then your factor will become, for the first 0 0 we have this equation, and for half for this, outside the half you can calculate, this is the iota pi. So this is the total scattering factor for BCC. So there are two cases arise, is that if the exponent, that is h dash k dash l dash, in the previous equation we have, this is, if this is very very important, this will decide the game. If we have h dash k dash plus l dash, so this is because this is, if this is the odd number, that is, yes, this is, sorry, this is 1, this is 1, this is minus 1, this is minus 1 for odd and plus 1 for even. Can note it, this is minus 1. So if this is the case, then again exponential iota, that is minus 1, this value tends to minus 1, then tends to 0. It means reflection like 1 0 0, 1 1 1, 2 1 0, etc. missing of the spectra. Okay. Now if this term is even number, then this will definitely equal to 1, then this term equal to 1. So this is 2f, and the intensity will be f star into f. So this is 2f into 2f, that equal to 4f square. So it means reflection light, this is 1 plus 1 plus 0, that is 2, even, this is even, this is even, these are present. So these planes are present in the system. Okay. So this is the case number 3. Case 3 is the case 3, structure factor for FCC crystals. For FCC, their effective number of atoms for FCC crystal is 4. If assuming that atom lies at this 0 0, first atom, another like face, from face is, there is like this, because faces we have only the two faces, they are adjacent to each other, so third atom is absent. So this is half half 0, this may be this situation, this may be this situation. So we have this is the first atom coordinates like this, the second atom coordinates like this, third atom coordinates like this, and this is the fourth atom, this is the fourth atom. First atom the coordinates, then second, then third is the fourth atom. On putting all the values in your summation, Total scattering factor is given by this and this, and on solving this, what we have, this is our final value, and here h plus k dash is the term, here h dash plus l dash is the term, and here k dash plus l dash is the term. So this is the total scattering power for FCC. So then there are different cases arises if h dash k dash plus all are odd, and overstructure intensity is given by, yes, if they are all are odd, if they are all are odd, then if this is 1, this is 1, I am taking the example of 1 1 1 like this. So 1 plus 1 1 plus 1 1 plus 1, so intensity will be, because this is even, so this is 1 plus 1 plus 1 plus 1, 4f, so intensity will be 4f square, that is 16f square. Similarly, if these are all even, then we can see if these are all even, if I can take the case of 2, then this is 2 plus 2, all even, 2 plus 2 like this, 2 plus 2, again we have got the even, and if the even, then iota n pi that equal to plus 1, and then our term will be again equal to 16f square, and f equal to 4f, so इसका square, that will give the intensity. And finally, this is h dash k dash l, if they are mixed, then if they are having mixed number, then the overall structure will be like this. If this is the case, you have a plane like this, then if then you, this becomes 2 plus 1 2 plus 1, because this is 1 plus 1, this is h plus k hai, there is h plus l hai, there is k plus l hai, like this. So this is iota 3 pi, this is iota 3 pi, this is iota 2 pi. So this is equal to minus 1, this is equal to minus 1, this is even, this is equal to plus 1. So if this is the case, then what we have, then f dash that equal to 0, and total intensity. So what we conclude, that in FCC structure, reflection like 100, 110, 211 are missing. These are missing due to mixed. These are mixed, odd, even, even. This is odd, odd, even. This is even, odd, odd, like this. Mixed fraction there, they are missing. But reflections, if they are completely odd or completely, these are completely odd or completely even, they are even, they are present in their spectra, X-ray spectra. So this is the total discussion, and I can also ask the question like this: calculate the structure factor for various 3 types of cubic crystal: primitive, that is simple cubic, body center, face center, and determine the reflection would be absent, which reflection would be absent from the fraction. The fractional coordinates of the atom in 3 types are given, that this one is, this is, and this is for simple cubic, this is for BCC, and these are for the FCC. This is simple, this is BCC, this is FCC coordinates, and I can ask this question. My dear students, I want to stop this topic here. Yes, this is the graphical representation of any one of my students' work of MSc. We are observing that there is 1 1 1, तो obviously this यहाँ जो आपके पास unit cell होगा, that is what type of completely, so this will FCC. So this is even, this is FCC, or this is simple cubic. There is BCC, something like this. We can see, we can determine the different planes by making use of structural factor. So thanks a ton, and if you have any query, you can ask. Thank you very much. you.